Hello and welcome to our MRAM forum panel discussion. Our topic today is what do we need to bring MRAM to the next level? Our session chair, Luc Tomas, is having some technical difficulties, so I will be stepping in for now to help. My name is Daniel Worledge, and we have a number of panel speakers who will be joining us today. Simone Bertolazzi, Gauri Sankarkar, myself, Daniel Worledge, Sung Kang, and Ko-Min Chang. First, we'll watch a short video from each of the panelists, and then we'll have the panel discussion.
Hi, my name is Simone Bertolazzi. I'm a senior technology and market analyst at YOL Development. YOL is a technology and market research company based in Lyon in France, with analysts spread all around the world and covering a variety of thematics in the semiconductor industry, including memory. Today, I'll be glad to share with you YOL's perspective on the evolution of the MRAM market, and I will address the question of this panel from a market analyst perspective. To this purpose, I think it's important to point out that the embedded and the standalone businesses can be very different. They have their own sets of challenges and strategies that players need to adopt for moving from niches to mainstream markets. The focus of this presentation will be on the embedded MRAM business. Here we see a clear opportunity for new memory, and this is related to the fact that eFlash, a mainstream technology for embedded applications nowadays, is hitting a scaling barrier. The cost of eFlash and the manufacturing complexity are becoming too high for nodes beyond 28 and 22. So there is a clear open way for new memories, such as, for instance, the MRAM. New memory technologies like the MRAM provides a good combination of properties like low power consumption, high speeds, high endurance, and long retention. MRAM, among the emerging volatile memories, has advanced at a relatively faster pace thanks to this combination of unique properties and thanks to the involvement of major players like foundries and equipment suppliers that are providing unique solutions to address complex technical challenges. Indeed, manufacturing MRAM is not an easy type of challenge and need to be addressed carefully, particularly as far as deposition and etching. I think it will be really important in the coming years to continue improving the tool throughputs, particularly for deposition and etching, in order to make high volume manufacturing a viable possibility for embedded MRAM. At YOL, we believe that foundries will play a critical role in the coming years for promoting and stimulating the adoption of MRAM, communicating about its key advantages and also delivering information about the reliability of the technology for applications that could also be part of the automotive market, for which high reliability is really necessary. So embedded MRAM will be at first a good opportunity for replacing eFlash at nodes of 28 and 22. And in the longer term, we also expect that embedded MRAM could be utilized as a last level cache type of memory, replacing EDRAM or SRAM. If we have a look at the market, I think the good news to share is the fact that embedded MRAM is currently in the market. We have a few products already. I can mention Sony's GPS that are utilized in Huawei smartwatches and are based on 8 megabit of embedded MRAM manufactured on 28 nanometer FDSOI at Samsung. Ambic also introduced microcontrollers for low power applications utilizing 16 megabit eMRAM manufactured at TSMC's 22 nanometer. There are other products that are expected in the short term, all involving new players in the field or startup, as well as leading foundries that are providing the manufacturing capability for these new products. I would like now to share with you YOL's overview and perspective on the overall market, standalone and embedded. In the standalone case, we do expect that the market has still the potential to grow up $300 million with a CAGR of 18% by 2026. It will be mainly driven by low latency storage, in particular hybrid drives that make use of MRAM for storage acceleration. We also consider a strong growth for the embedded MRAM market with a CAGR up to almost 90% until 2026. And the growth will be driven by microcontrollers, low power IoTs, as well as edge AI type of applications. The market is expected to grow also in terms of wafer production, and by 2026, you'll expect that up to 300,000 wafers could be produced by the industry, and these wafers will contain embedded MRAM. And with this, I would like to conclude this short presentation mentioning that all these analyses and results are part of YOL's report on emerging non-volatile memory. And YOL is also very active on other memory technologies, in particular mainstream NAND and DRAM. And with this, I would like to thank you all for your attention.
Hello, good morning, good afternoon, and good evening, depending on from where you are listening. My name is Gauri Shankar Kaur. I am thankful to the organizing committee to invite me to have a discussion on this exciting topic. Today, the topic of the panel discussion is what do we need to bring MRAM to next level. Let me first discuss about the main drivers of this technology. As you know, the servers, high-end system, and the GPUs, this entire system is suffering from the memory wall issue. So today the biggest challenge is to address this memory wall. One of the solution we do see that increase in high density last level cache. This can also change the cache hierarchy drastically, and we do see there is an opportunity to optimize the size versus power versus performance. What will be the requirement for that? It will be density, power, performance, and cost. The second main driver is the IoT and smart sensors. The question is how to enable the edge compute in this domain. Again, the need of this one is the low power, high density memory. It is possible to change the entire memory hierarchy from non-volatile latches and flip-flops to cache and the main memory. It can also enable normally off computing. It required lower power and lower cost. There are several niche applications. One of the emerging niche application is the in-memory computation. In this case, the same memory element capable of performing computation. Example, logic and the analog computation. It also requires different functionality, read versus write, and the density. Now let me summarize what are the main challenges and issues. The technology and the architecture aspects are the most important one. First question is the technology is ready. For high performance, what is important is the right speed versus the right margin. When we talk about the right margin, we refer to the margin between the breakdown voltage and the worst corner of the switching voltage. It is still is a big challenge. 2-bit ECC has been considered as a solution to address the bit error rate. In some cases, it is also considered the 4-bit ECC is also considered, but it causes huge overload burden. So ultimately, there is no area and density benefit. The fabrication cost is very important. It is important to keep the fabrication cost low, though there is a need of new materials, new process steps, and the new mask. Here the question will be, can off-chip embedded MRAM solution make it cheaper? Today, the classical cell is 1T, 1 MTJ. Transistor is used as a select device. This is not good enough. to have high density on and off chip embedded MRAM. We need two terminal high performance select device to make it 4F square compatible for high density cell. Also, there are few need in the system architecture. Compatibility with heterogeneous system architecture paradigm, which will enable hybrid memory hierarchy. Also, we do see competition from other technology. Example, SOT MRAM has higher potential to address the performance reliability issue, but it has its own problem, that is the bit cell size. The VCA SOT device could be a good solution to address the bit cell size and also the energy issue. But the spin hole angle efficiency and the VCMA coefficient of the stack are the biggest challenge. Recently, we do see that FERAM is making good progress, and this is a field-driven switching. FERAM was suffering from the scaling issue, but in recent research, we do see a good progress both in the size scaling and also in the voltage scaling. Here, the new memory technology, MRAM technology, VCMA, could be a good competitor. That's still the future will say. With that, I conclude my talk. Thank you.
Hi, I'm Daniel Worledge from IBM Research, and I'm going to talk about what we need to do to bring MRAM to the next level. The first type of MRAM application is standalone memory. Here there are lots of good applications for MRAM in use today. For example, using MRAM as a buffer for solid-state drives. For example, IBM uses Everspin's MRAM in their flash core module. And the requirements for this memory are listed here. And one way that standalone MRAM could be improved is by going to higher endurance above 10 to the 10th cycles and better write error rate lower than 10 to the minus 11. Another way you could improve standalone MRAM is to make it dense. In fact, so dense eventually try to replace DRAM. I don't think that's realistic at the moment. I don't see MRAM replacing DRAM anytime soon, unless DRAM runs out of scaling at some point. But making MRAM denser would certainly make it better standalone memory. And for that, the key thing to do is to reduce the switching current. And that's because the area of the cell is determined by the transistor used to access that device. And so if you can reduce the switching current of the MTJ, that will allow you to reduce the area of the transistor that is used to source that switching current, make the MRAM denser. The second category of application is embedded non-volatile memory, ENVM. And this is what all of the major foundries are working on or offering, Samsung and Global Foundries and TSMC. And this requirements are shown here, and one way to make embedded non-volatile memory better will be to move to even higher temperature ranges, up to 150C and 175C and so on. The third application is mobile cache. I consider this to be the killer app for MRAM. It's to replace both SRAM and flash in embedded applications for applications that really value low power and don't need very high performance. So for example, in Internet of Things, where you have a remote device that's powered by, say, photovoltaics, you can save a huge amount of power by not having to write data back and forth between SRAM and flash, but instead use MRAM in place of both. Use the MRAM as the working memory in place of the SRAM. It won't be as fast as the SRAM, but fast enough for these applications. And that low power will allow you to do things you couldn't otherwise do. So we're not quite there yet to make MRAM good enough for mobile cache. Some of the challenges are to get fast enough read and write down to 10 nanoseconds and then maybe 5 nanoseconds, and also to improve the endurance up to 10 to the 12th and higher. And the last type of application is last level cache. So this is basically L3 or L4 cache, what people have used embedded DRAM for in the past. Last node for embedded DRAM will be 14 nanometers. And at more advanced nodes, there is no embedded DRAM, and other foundries don't have embedded DRAM. So if we could develop MRAM that could be dense enough and fast enough to be used as last level cache, that would be of great value. But the challenges there are very high. We're not ready for that yet. We need to have very high density. That's the main challenge. We've demonstrated fast read and write and high endurance, which are also challenging. But the density is the key thing. Even though the cell of the MRAM is quite a lot denser than SRAM, at the macro level, you still need to be 2 or 3 times denser than SRAM. That can be challenging unless you can get the cell to be many times more than that denser. So again, the key there is to reduce the switching current. We can reduce the switching current by about a factor of 2. That would open up these last level cache applications. Thank you.
Hello, MRAM Forum participants. I am Song Kang from Qualcomm. It's my pleasure to be part of this panel session. Let's overview how MRAM's doing and what shall be done for MRAM to move towards the next level. MRAM, here perpendicular STT MRAM, has a long history of ups and downs. Now, about 10 years after the Tohoku University researchers published cobalt-ion boron perpendicular MTJ paper, the ecosystem has been fully established. This is remarkable since not so long ago, there was high skepticism in the semiconductor sector about if such MRAM would be ever manufacturable. In contrast, the world's top 3 foundries currently offer not only production, but also turnkey design IP. The tool suppliers brought essential contributions through persistent investment. We have seen the emergence of IP design houses. Meanwhile, a slew of product companies are seeking MRAM for applications such as IoT, wearables, automotive, and enterprise infrastructure. Finally, the MRAM research community remains undeterred, driving innovations on advanced MTJ and SOT MRAM. However, few would disagree that MRAM has not reached fruition as the community long promised and anticipated. First, the product adoption has been very slow and much limited. Ironically, the reason may not be the technology itself, but still a hesitance or even fear about adopting something new. Note that most of the product companies are new to this technology, and in general, semiconductor industry is not a fast adopter of something new, especially where incumbent technologies are still good enough to use. This situation is not being helped by limited MRAM offerings from foundries, driven by more traditional embedded non-volatile memory markets. All 3 foundries offer MRAM as embedded flash alternative. Though better scalable and with better PPA, this MRAM is not close to the promised version. While this is happening, the node gap between MRAM and the logic is widening. Logic products are already at 5 nanometer and 3 nanometer likely emerging next year. For MRAM to be a pervasive technology, it is critical MRAM to go beyond eFlash applications and also to overcome such node gap. Keep in mind that no memory supplier forces MRAM as a commodity DRAM or mass storage flash replacement. If MRAM wants to be in the game, it has to do with logic SoC. So my feedback today to the MRAM community is summarized in 3 points. First, we focus on MRAM's inherent advantages over other memories. MRAM is a new class of memory that has a combination of high performance and high endurance with non-volatility. By far, no NVM can reach below 10 nanosecond read and write speeds with billions or trillions of endurance cycles. Second, bridged the node gap through system integration. In the foreseeable future, it doesn't seem feasible that MRAM is embedded into 5 or 3 nanometer SoC. However, such nodes, also very challenging even from the SRAM point of view, would get the benefit of MRAM as a discrete chip, but integrated in a system. Third, innovate with purpose. Drive engineering solutions. The research community should help advance MRAM, for example, to realize SRAM like MRAM. In addition, SOT promises solving inherent challenges, but we shall turn it into a useful form, scalable, faster, and more reliable. Finally, go small. Improve PPA by reducing the MTJ size and switching current and voltage. In my opinion, this has been the most difficult technical challenge for over a decade. Yet, without a significant breakthrough from the research community. With that, I look forward to entertaining discussions. Thank you.
Hello. First of all, I'd like to thank Bernard and Luke for inviting me to be part of this panel discussion. My name is Koming Chai. I'm with the NXP Semiconductors. So let's talk about what do we need to do to bring MRAM to the next level. I would like to invite you to envision what this next level may look like 5 years, 10 years down the road. As you can see on the left column, under the next level, you see next level in terms of technology, in terms of markets, in terms of supply chain, in terms of financials. And across the top, you see NVM 2020, you see MRAM today, 2021, MRAM 2025, and MRAM 2030. So I will start with the column with MRAM today. So again, I'm offering my view from an embedded user perspective. So with that, I see that I need a solution with good speed, with low power, with good endurance. But I'm not finding too many options. I think that is one of the reasons that's constraining the market to be confined to some embedded specialty markets based on what's announced. And also, in general, there's this magnetic immunity thing that's hanging over. So, and also from a user point of view, I'm looking for markets based on and I find it very disjointed. I see various wafer foundries. I see various IP houses. The solutions are not always well integrated. And also, the financial side, the cost is not helping. So really, I see what we need more visionary pricing strategy moving forward. Look at the column to the left. Just use NVM as a reference. NVM includes NAND, NOR, SCM. Now, this is a lot of good technology advancement thanks to the process design interplay, and which resulted in a very broad-based marketplace, standalone embedded, and take NAND as an example. There's only a handful of suppliers that are highly vertical, and which also drives the commoditized financial behavior, which is a sign of a good mature market. And so fast forward 5 years, I would like to see that there are many products and demonstration of energy efficient solutions that are mature, that are reliable, and also safe and secure against cyber attacks, for instance. And I continue to see embedded dominate the markets. Love to see some standalone solutions out there. And from a supplier point of view, really there's a lot of geopolitical factors So as a user, we need to think about that. We see multiple source solutions, and from a financial point of view, I see some alliances forming in order to achieve economy of scale, and also to help to verticalize the supply chain. That will fuel the further growth. So in 2020, with many offerings of different flavors, I would like to see that the tech community here continue to have magnetics-based ideas that offers better KPIs, just to show that the technology is scalable to fuel the growth till 2040. So will the MRAM stay at the time, 10 years? I think so. But that's my faith statement. A lot of things need to happen within the 10 years, including moving more towards standards-based supply chain, because I think that is a key. And as a result, the market can be more commoditized. Users like me, I can pick and choose the suppliers based on what I need geopolitically and so on and so forth. So I think that would be a sign of a good, mature technology capable of serving a much bigger SAM. So I will stop here.
Hello, everybody. Yeah, I am very pleased to join the panel discussion, and I'm very sorry for the technical problem that we had at the beginning of this panel discussion. And our moderator, Luc Thomas, had a serious connection problem. So I'm stepping in, and I thank also Daniel for starting the session. Yeah. So thank you very much for your presentations, and to the five of you. And I really like to welcome you to this panel discussion. And now we can open the discussion, and so all questions are welcome, and you can ask a question in the Q&A chat box. And so each of your presentation actually raised questions, and maybe I will start by asking question to Daniel about you mentioned, Daniel, that standalone memory, MRAM memory, are not going to replace DRAM anytime soon. I have seen in the past some concept of a hybrid memory in which a DRAM volatile part was mixed with MRAM non-volatile part, and to make a kind of a hybrid volatile non-volatile memory. Do you think this kind of memory can have a future soon?
Yeah. A hybrid memory, that's an interesting concept. You mean like literally fabricated on the same chip? Because that sounds expensive. You'd have to make a DRAM process and then an MRAM process as well. That I think is a little unlikely. I could see package solutions, 3D integration, and combine these two together. That's definitely a promising direction.
Okay, yeah. And but to go towards this standalone application, yeah, the main difficulty is the patterning at high density, I suppose, and high density, small pitch, and so on.
Yeah, I mean it's even more than that for MRAM to be able to compete with DRAM on density. We'd need to have a much smaller cell. As I mentioned in the video, to have a much smaller cell means the transistor, the access transistor, will be smaller, and then it won't be able to source the drive current to write the MTJ. So we're really not limited by the size of the MTJ itself or the patterning of the MTJ as much as we are by the write current of the MTJ. So if we could invent new materials that write with much lower switching currents, then we'd have a shot at competing with standalone DRAM.
Yeah. Actually, yeah, in the talk, the presentation by Gauri Sankar, yeah, you mentioned, Gauri, the VCMA right approach, and do you think this this could be used sometime? The VCMA, what needs to be done around the voltage control of magnetic anisotropy?
I would like to start with what Daniel just mentioned, that the transistor, if you stick to the transistor, I think it is impossible to catch DRAM density. Because if you look, the DRAM transistor itself is so optimized today because you don't care about the performance of the transistor anymore to have the DRAM speed. What you need then to make sure that you switch it on and off, and you have almost like a less than 10 microamps per cell current to drive the DRAM, get the DRAM read write speed. So with a transistor MTJ, I do not believe that ever MRAM will able to catch DRAM density. If we want to go to the DRAM density, what is needed is the selector. You have to find a two-terminal selector device to couple with MTJ device. Let's start with STT first. Combined with that one, then only you can go for the density. You can catch the density there. And of course, as we are talking about the power, and I think that not me, at least the community believe that the VCMA could be one of the best option there. But of course, it suffers from the PCMA coefficient, all the other parameters also. So it's a long way to go, but best thing will be to start with selector plus MTJ as a high density application.
Okay. We have a question from Qing Xiang to Komin Chang. What is your idea about using MRAM in the auto MCU? When do you expect it available for auto grade?
Well, it's a very relevant question given the challenge to the auto components these days. So actually, I think MRAM for auto application is imminent. I think it in itself is already auto capable, especially when it's used in an MCU type of application, used as a flash type. It's got good enough thermal stability. It's got it's fast enough. It's low power enough. No, I think it in itself is auto worthy. Of course, and when we talk about auto worthy, there are some auto specific things that needs to be built into the design. So it's not a simple technology question, right? And for auto, you have to worry about the functional safety. How do you design your system around it, and so on and so forth. But fundamentally, I think MRAM for auto is I don't think it's a problem.
And there is a related question from Fang Zhu to also to you, Komin, and but if the others want to comment also, how has the electrical vehicle market changed the automotive MCU requirements?
Well, certainly the EV is really opens up a whole new opportunity, right? Because you just look at Tesla, look at NIO, all these new players, right, as opposed to the traditional ones. In order to perfect engines takes a tremendous amount of resources and energy and time. But the EVs are. I say it lightly, but it's just you control a few motors, right? And of course, the other things is with the EV, how do you control these? With EV, it's a battery, right? It's safety wise, it's a battery management, and so that is very critical. And also how to control, how to monitor and continuously control the battery performance in order to extend the driving distance, right? And those are the elements that make and break a EV brand. On top of all this hype about autonomous driving and things like that. Keep in mind, Tesla is getting a lot of the attention, but from an automatic driving perspective, it's only at level 2, so it's not very advanced, right? So so EV is coming, no doubt about it. And I think MRAM should be as ready as the combustion chamber-based cars. So
does the EV market change the temperature requirement though? Do you still need 150C or is 125C good enough?
I think EV lowers the temperature requirement. Yeah, so I think that's a golden opportunity.
Mm-hmm.
Yeah.
I think many people
Okay.
simply forget about there are many different grades of auto applications. 150 is only for the extreme ones. And probably the number of chips, about amount of chips that serve that need shouldn't be that big, considering the overall auto grades, especially lately, right?
Yeah, I mean, Daniel, the high temperature requirements are mainly around the powertrain, right?
Yeah.
Around the engine
Yeah.
and the transmissions, and so yeah, you replace it with motors. It's a whole new game.
Yeah, we've heard many times that the market at 125C is much larger than the market at say 105C. Does anyone have a sense of how much larger? Is it twice as large, 10 times as large? And at 150C, it's not significantly larger than at 125C. Is that's Sung what you seem to be implying?
Yeah.
No, I don't have a figure offhand. Yeah. No.
We have a question from Jack Gage to Seung Kong and Guri. What are the main challenges to have MRAM on smaller technology nodes like 5 nanometer, 3 nanometer?
Mm-hmm. Right. Corey, you want to go first? Should I go first?
No, you go.
Yeah, I
boss.
mean, that's something that, kind of ironic that when I was involved in MRAM development more than like about 15 years ago, our company moved directly to 45 nanometer. Why? Because that was the bleeding edge node at the time. So right now, the bleeding edge node is 5 nanometer. And as I mentioned in my talk, 3 nanometer is coming along next year, right? So the difficulties is mainly about MRAM scalability or MTJ scalability, as I see. So, because as logic node progresses, that alone is extremely challenging. If you look at the SRAM scaling, it's like a DRAM, that 6F square, 8F square number is always maintained. SRAM cell size relatively grows a lot. That's an indication of the difficulty in logic alone. So adding an MTJ to the already difficult logic is extremely challenging. I mean, the logic folks, right? Their hands are already full. So when small MTJ is ready, it can switch fast. It can be integrated in a smaller form factor. Then they will welcome it because it's a backend memory, so they can add this MTJ at the back end of the line and then just connect it to transistor and things will work fine. But right now, the biggest challenge is switching current is too high. Related, MTJ size is too big. So those things are main factors that the advanced logics cannot adopt this MTJ, right?
Okay.
Yeah,
I agree with Song.
I may add few comments here. So what Song mentioned, that is absolutely right. But on 5 and 3 nanometer or 10 nanometer, what application you are looking for? So example, there are two applications, right? We are discussing. One is an embedded flash. Second one is the last level cache kind of application. Embedded flash, there is no need because technology is still hardly at touching 45 and going to 28. So there's a huge gap between the advanced logic and the embedded flash technology requirement. Now coming to the eFlash, for the last level cache, as we discussed, the technology itself is not ready. There is a power problem, there is a performance problem, there is an error issue. There are a lot of issues still there that those needs to be solved before you can address it. Then the third component is the cost overall. Because bringing this technology to 5.3 nanometer, you imagine that you have to add it in the back end, and it's a huge cost. Foundry is asking huge amount of cost for that, and we do see there is actually potential solution here. And Xiong mentioned, I also briefly touch it in my talk, that going to the 3D, basically you take your off, if you take your last level cache as an off chip, you go to the older generation technology node, you actually can solve both problem. You can solve your cost problem, and the second thing, you can solve your also the current issue also, because older generation, you have a bigger transistor, you have a higher current, you have a solution there. And then you bring them, do the partitioning work, and bring them and put them together using the TSV technology. That could be an alternative solution moving forward. Otherwise, catching the 5.3 or even 2 nanometer, 1.5 nanometer, it's impossible for MRAM. I don't think that we are ever going to solve that gap.
Even without MRAM, I think there is an active, work going on to split the
Exactly,
logic die into
exactly.
multiple dies.
SRAM
Right?
is already partitioning,
Yeah.
actively going there.
Yeah.
You see
I
the
think
hot chip
that's
conference,
a
many.
that's a very good news for MRAM, because once the embedded MRAM is ready, for example, at 5 nanometer, or logic already moves to 3, right? So you miss the boat.
Exactly.
That repeats. However, in this case, you develop it at, 10 nanometer FinFET or 7
Yeah.
nanometer FinFET. You can attach them together.
Right.
Yeah.
Absolutely. And you
Yeah.
get the cost from the node perspective. You gain the cost from the number of metal layers perspective, because in an
Sure.
advanced logic, you need 20 up to 20 metal layers. Only for the embedded memory block, you need maximum 3 to 4 metals. So you have additional 15,
Correct.
16 metal on
Yeah.
top of the memory block, just for the nothing actually there, honestly speaking. So you have a huge gain in the cost side also.
Okay, thank you very much. We have a question from Yuan Jen Li to Simone. How does semiconductor shortage affects on MRAM development?
Okay, so thank you for this question. I think it's good to have a broad picture in mind when we discuss also about MRAM and in general emerging technologies and so on. So I do believe that the research and development projects and also the activities related to MRAM can continue, although it's clear that foundries and also other players within the semiconductor supply chain have shifted their priorities. So there's really need to catch up on certain production of semiconductors that are critical, particularly for the automotive space, as we discussed before. So I believe that there will be pressure on the foundries now to catch up on on serving the automotive market. And certain projects could be somehow delayed, but the impression that we have at YOL is that most of these research and development projects and also the ramp up of embedded memories in microcontroller application on IoTs can continue, although some delays clearly need to be expected.
Okay, thank you. And Gori, in your presentation, you mentioned that MRAM are competing. They are competing technology, like in particular ferroelectric memory. How would you compare the advantages of ferroelectric memory and those of MRAM? And do you see specific field which would be better covered by one or the other technology?
So, as you know, in the ferroelectric also there are very many flavors of devices. They have this ferroelectric FET, ferroelectric RAM, and the ferrotunnel junction, which the new one is concept is coming. And if you look backward, actually the ferro RAM is not a very old, a new technology. It's a very old technology. It's also in the production for a long time. Many companies are producing. And the challenge in the ferroelectric RAM was the scaling. But with the new class of material, people are making a lot of new researches, and the new class of material is coming out. And there we do see that the ferroelectric RAM is also scalable in terms of the size and in terms of the voltage, because that was the two major challenges there. Now, if it is true and if it is really meeting, and we do see the performance is there, you have the speed there, you have the endurance there. Even this is a field-driven switching, so you have even the lowest power there compared to the MRAM. MRAM is a switching, current-driven switching. This is a field-driven switching. So you have all the advantages there. So if it happen, even in the embedded domain, example, IBM and Intel, they had this embedded DRAM and they stopped it because of the scaling issue. They couldn't scale it. And if the ferroram is coming there, you can consider again a 1T, 1C structure as a ferroelectric embedded DRAM also. This is definitely one thing. Also, it can go even for a DRAM also, because it's the same not exactly the same device, but the same family. Is instead of a dielectric based capacitor, you are moving to the ferroelectric based capacitor. In the DRAM domain also, you can go there. Transistor requirement is much lower because is not suffering from the leakage issue anymore. So definitely it's going to be a tough competition, I think, in the longer term. But MRAM has an advantage because it's already quite matured in the foundry and in the industry. And the ecosystem particularly is all set already. So that advantage is there, but we have to maintain this advantage. Otherwise, someone will take this advantage from the behind.
Yeah, I do understand. We have to keep the momentum here.
Exactly.
Okay. There is a question from Meng Zhu to Daniel and Seung Kang. What is the current performance of MRAM in terms of SRAM replacement, and what are the targets? How far away we are from these targets?
So maybe I can start there for replacing SRAM in last level cache. That's like the most advanced MRAM application we've got, the hardest one. We're still some ways away from meeting the requirements there for MRAM, and the key thing is reducing the switching current. It's a density question. The SRAM, is a 6 transistor cell or 8 transistor cell, but the efficiency of the memory is very high. There's not a lot of peripheral circuitry in SRAM. But in MRAM, there's a lot of peripheral circuitry. So you have to consider not just the area of the array, but also the area of that peripheral circuitry. So when you compare that fairly, we still need to reduce the switching current by roughly a factor of 2, say, to have a shot at competing with SRAM in last level cache. That's the bottom line. So not quite there yet. The trade-off, of course, for last level cache is that the MRAM will always be a little bit slower than the SRAM, and we're going to compensate for that by being much denser. So it's not sufficient to be as dense as the SRAM or a little bit denser. You need to be 2 to 3 times denser at the macro level.
Okay. Seung, do you want to
continuing
add?
that, probably at the advanced node, the bit cell size would be about 1/3. The MRAM size is about 1/3 of SRAM. So when you build relatively conservative macro with error correction circuits and everything, chip area, the memory chip area is probably about a half. MRAM will be about half of the SRAM. So this kind of thing is very important when you build a very large density memory, like an L3 cache. As the density increases, what Daniel mentioned in terms of performance, even in power, MRAM brings advantages because cell level switching, matters, much less when the memory density becomes larger, because SRAM is also affected by a lot of parasitic delays and additional power consumptions as well. So when we did the exercise, we saw about 5 nanosecond read speed, read cycle time, which is doable. Write was a challenge, but the L3 cache write is not really driven by the cell speed. Through the architecture optimization and system level optimization, maybe like slightly under 10 nanosecond or so, you can actually pretty much match SRAM's last level cache performance at the chip level. Yeah. But the challenge was how to secure a sweet spot for this kind of read and write speed, along with, let's see, like tens of megabits of large density with maybe like 10 to the 11, 10 to the 12 cycles of endurance. So hitting all these things together at the same time, that was a technical challenge.
Okay, thank you very much to both of you. So time is flying, and I think it's now time to end this panel discussion. And so I'd like to thank you very much, panelists, to be there and answering the questions and leading these discussions. And I hope you enjoy this 12th MRAM Innovation Forum. And again, the next the next forum will be organized this time next to IEDM, so in December 2021. We don't know yet whether it will be in person or again online, but we will keep you a brief.
So
So
we'll have two
thank you.
forums this year. So this one and IEDM.
Yeah, and another one in 8 months at
Oh, wow.
IEDM. Yeah. Okay, so thank you very much, and hope to see you again very soon, and enjoy the Intermag conference. During Intermag, yeah, I remind that there is a special session on STT-MRAM, another one on SOT-MRAM, and overall around 200 talks related to spintronics, so plenty of things to see and to watch and discuss during the conference. Thank you very much, and bye-bye.
Sure.
Thank
Thank
you.
you.
Bye.
Bye-bye.
Maria.
Bye.
Bye.